Welcome to the video lecture on implicit differentiation. Implicit differentiation is a new technique that we're going to learn to be able to take derivatives of curves that are not solved explicitly. Now, an explicit equation is something where you have the y variables solved on one side of the equation and everything else in terms of x is on the right side of the equation. So if you saw 3x minus y minus 2 equals 0, that would be called an implicit equation because the x's and the y's are sort of mixed together on both sides of the equation. But it would be pretty simple to solve this for y by just adding the y over to the other side, and that would give us that y is equal to 3x minus 2. So this side is called explicit versus this side, which is called implicit. We know how to take derivatives of explicit things, like this one, 3x minus 2. We have derivative rules that would tell us that the derivative of that would just be 3. So that's really easy to do. But we don't have necessarily yet a method for taking a derivative of something that's written implicitly. Let's take a look at this next example. xy minus 1 equals 0. Again, that's an implicit equation because the x's and y's are sort of mixed together. But if I add 1 and then divide by x, that gives me that y is equal to 1 over x. And we know how to take the derivative of that because you could just change that to x to the negative 1 and use your power rule. So again, we have a way of taking derivatives explicitly, but not necessarily implicitly. The next equation here, x squared plus y squared equals 36, is just the equation of a circle. So to solve that for y, we could subtract the x squared and then take a square root of both sides. And remember, when you take a square root of both sides, you need a plus and a minus square root. So explicitly, this would be plus or minus the square root of 36 minus x squared. And that would require using the chain rule to take the derivative of that. Now, if you look at this last equation here, this is another implicit equation because the x's and y's are sort of mixed together. And you can see that it would be really difficult, if not impossible, to try and solve this for y because we have that y cubed in there as well as this other y term. So it would be really difficult for us to figure out a way to solve this for y. So this implicit form right here is kind of what we're stuck with since we don't know how to turn it into its explicit form. So if we really needed to know what the equation of the tangent line was or what the derivative was, we wouldn't have a way of doing it explicitly. So what we're going to do is learn a method called implicit differentiation, which will enable us to take the derivative of something like this directly and figure out what that derivative is. Now when we do that, what we're going to have to do is take derivatives of x terms as well as y terms. And when we take these derivatives, we're going to be taking the derivative with respect to x. So if you're taking the derivative of an x term with respect to x, then that's just going to be the normal derivatives that we're used to. But when we take the derivative of a y term with respect to x, that's going to require our chain rule because y is going to be implicitly defined to be a function of x. We just don't know what it is. So we're going to have to be really careful when we take derivatives of those y terms. So for example, if I wanted to take the derivative with respect to x of x squared, then that would just be the normal derivative 2x. But when I want to take the derivative of y squared with respect to x, you have to think of this y as sort of an inner function of x. We just don't know what its formula is. So to take the derivative of y squared, it requires the chain rule, where first we take the derivative of the outer function, which is that square. So we bring down the 2 and we subtract 1 from the power. What's inside stays inside. And then we multiply that by the derivative of this inner function y. And since we don't have an actual formula for what that y is, the best we can say is that the derivative of y with respect to x is just dy dx. So the end result is that when we take the derivative of this y squared term, you're going to take the derivative of y squared just like you would expect, so 2y, but then you have to multiply that by a dy dx, or sometimes we multiply it by just y prime. You can use either notation, dy dx or y prime. So the end result here is that derivatives of x terms are going to be the normal derivative. Whenever this variable down here matches this variable here, you take the derivative like you normally would. But when the variable down here does not match the variable that you're taking the derivative of, you need to use the chain rule. So you take the derivative like you normally would, and then just multiply that by a dy dx or a y prime. So the process of implicit differentiation is used to find dy dx in situations where y is not explicitly defined as a function of x. If we wanted to find the slope of the tangent line on the curve 2x squared minus 3y cubed plus 2y equals to 2 at the point 1, 0, we could use implicit differentiation to find the slope of the tangent line. And in using implicit differentiation, we just have to realize that when we differentiate functions involving x's alone, we differentiate as usual. But when we differentiate functions involving y, we need to realize that y is a function of x, and therefore the chain rule needs to be used. And that's why we're going to be multiplying any y terms by the derivative dy dx or y prime. So here's our process. To take the derivative of an implicit function, the first thing we're going to do is differentiate both sides of the equation with respect to x. Then we're going to collect all the terms having a dy dx on one side of the equation and all the other terms on the other side of the equation. Then we're going to factor out our dy dx, and then we're going to divide both sides of the equation by that coefficient so we can get the dy dx by itself. So let's go ahead and find the equation of the tangent line to 2x squared minus 3y cubed plus 2y equals to 2 at the point 1, 0. Now remember, if you want an equation of a tangent line, you need a slope of a tangent line, and a slope of a tangent line is a derivative. So that's why we're going to be needing to find the derivative of this equation first. So how do we find the derivative? Well, we need implicit differentiation because these x's and y's are sort of mixed together. We don't have it equal to a function like y equals whatever. So step 1, take the derivative with respect to x of the left side of the equation and set it equal to the derivative of the right side of the equation. You have to do it to both sides. Now here's the rule. If you're taking the derivative of an x term, you take the derivative as normal. If you're taking the derivative of a y term, you take the derivative as normal, but you multiply that term by dy dx or y prime, and that's because of the chain rule. So the derivative of 2x squared with respect to x would just be the normal 4x. But then when we get to this 3y cubed, to take the derivative of that y term with respect to x, we have to use our chain rule. So the 3 would stay there, but when I use my derivative rule and take the derivative of that y cubed, I'd bring that 3 down. It would become a 9y squared. That's what the normal derivative wants to be, but because we don't know what that y function is, we have to multiply this by dy dx. Okay, so similarly, when I get to the 2y, take the derivative as normal. So the derivative of 2y wants to be a 2, but then we have to multiply that by a dy dx as well, because it had a y term in it instead of an x term. And then on the right-hand side, the derivative of 2, that's just a constant, so the derivative goes to 0. So that's step 1, taking that derivative. Step 2, we're going to get these two dy dx terms by themselves, so we need to move this x term over to the other side by subtracting. So I'm going to have negative 9y squared dy dx plus 2 dy dx equals negative 4x. So now we have the two dy dx terms together. Step 3, we want to consolidate the two dy dx's into one, and we can do that by factoring. So I'm going to factor out a dy dx, and that will leave me with a negative 9y squared plus 2 equals negative 4x. And finally, step 4, we're trying to get the dy dx by itself. So what we can do is divide both sides by that stuff in parentheses, and that will get us that dy dx by itself is negative 4x over negative 9y squared plus 2. Now this is just an option, you don't have to do it, but if you wanted to kind of clean this up a little bit, you could multiply the top and the bottom by negative 1s, and that would give us that dy dx is equal to positive 4x over positive 9y squared minus 2. So that's called implicit differentiation, when you're taking derivatives of x's and y's simultaneously, and then you're solving for that dy dx. The only part of this process that's actually the calculus step is this first step when we do our derivative. The rest of this is just algebra and solving for dy dx. Now, we found our derivative. That derivative represents the slope of the tangent line at any point. We want the slope of the tangent line at 1, 0. So what we're going to do next is we're going to take this derivative and we're going to plug in this point 1, 0. Now normally when we're finding slopes of tangent lines, we would just plug in the x value and we would have our slope. But remember, this equation was implicit to begin with, so that's kind of why the derivative is implicit as well. It involves both x's and y's in the answer. So when we want to find the slope at the tangent line at this point, we're going to have to use both the x value here and the y value here. We have to use both of them. So this slope, m, becomes 4 times 1 over 9 times 0 squared minus 2, which is 4 over negative 2, or negative 2. So now we know that our slope of our tangent line is negative 2, and we know that we're going through 1, 0. So putting those two things together using point slope form, we can find that the equation of the tangent line is going to be y minus 0 equals that slope negative 2 times parentheses x minus 1. So we get y equals negative 2x plus 2, and there is our tangent line. Okay? All right, let's try this again. This time we want to find y prime in the following. So we have x squared y plus y squared x is equal to negative 2. So we're going to need to use implicit differentiation again because I have x's and y's mixed together. Now this example is a really important one, and it's often something that causes common mistakes by students. When we go to take the derivative with respect to x of both sides, look at those x squared y and y squared x terms. What we don't want to do is take just the derivative of the x squared and multiply that by the derivative of the y term. The reason we don't want to do that is because what's implied in between that x squared and that y is multiplication, and the same is between y squared and x. So these are products of two different terms, which means we have to use the product rule. And that's often overlooked. So you have to be really, really careful and look for that whenever you have x and y terms mixed together being multiplied. So we're going to need to apply the product rule to this x squared y, and then we're going to need to apply the product rule again to this y squared x. So the product rule goes first times derivative of the second plus second times the derivative of the first. So that's what we're going to do to this first term. So the first would be this x squared times the derivative of the second. Well, the derivative of y with respect to x is just dy dx, because the derivative of y wants to be a 1, and then we want to multiply that by that dy dx because of the chain rule. So far we have the first times the derivative of the second plus the second, which is that y, times the derivative of the first. Now the derivative of x squared with respect to x is just going to be a normal 2x. Remember, when you're taking the derivative of x terms, you take the derivative as normal. When you take the derivative of y terms, you take the derivative as normal but multiply by dy dx. Alright, so there is the product rule for just this first term. Now we need to do the product rule for this second term. So I'm going to add to this and do the product rule over here. So it's going to be the first term, which is y squared, times the derivative of the second. The derivative of x with respect to x is just a 1. Plus the second times the derivative of the first. The derivative of y squared wants to be a 2y, but we have to multiply that by a dy dx. So there's our product rule for the second box. And finally, the derivative on the right-hand side, that's just a constant, so that's going to go to 0. Now, instead of writing these dy dx's, which gets a little clumsy sometimes what we do is just write y prime instead. So this second line here could be written the same as x squared y prime plus y times 2x plus y squared plus x times 2y y prime is equal to 0. So I just used y primes instead of dy dx's. It doesn't matter which notation you use, it's up to you. Now once we have our derivative, we want to clean it up a little bit. So this is going to be an x squared y prime plus 2xy plus y squared plus 2xy y prime equals to 0. This term here and this term here have y primes. So the other two need to move. So I'm going to subtract both of these to the other side. So we get x squared y prime plus 2x y prime equals negative 2xy minus y squared. Once you get your y primes together, we're going to factor it out, and in parentheses we're going to write what's left. And last but not least, we'll be dividing by that stuff in parentheses. So our final answer, y prime, will be negative 2xy minus y squared over x squared plus 2x. And it's pretty typical that your answer for these derivatives will have x's and y's together because your function originally, or your curve originally, had x's and y's together as well. Okay, let's try this again. Here we want to take the derivative of the square root of xy equal to x minus 2y. So again, the x's and the y's are kind of mixed together here. It would be really difficult to solve this for y, so we need to use that implicit differentiation. So we want to take the derivative with respect to x of both sides. Now when I see a square root, I immediately like to change that to a 1/2 power. So I'm going to change this this left-hand side to xy parentheses raised to the 1/2. And then I'm going to need to take the derivative of the right-hand side as well. Now the left-hand side is kind of complicated. Right away, you should notice that you have an xy right next to each other. So there is implied product in between. So we are going to need a product rule here for that x times y. But in addition to that, we have this outer function, this 1/2 power on the outside. So that means we're also going to need the chain rule first before we even get to the product rule. So on the derivative of this left side, we're going to take the derivative of that outer power first, and then we're going to multiply that by the derivative of the inner function, which is where that product rule is going to need to come into play. So let's start on the outside. What would be the derivative of an outer power? Well, you bring the power down, and then you subtract 1 from the power. So the new power here would be negative 1/2. What's inside stays the same. So the inside needs to stay xy. Then the chain rule says multiply that by the derivative of what's inside. And to take the derivative of that xy, we need that product rule. which is kind of a big mess, right? So I'm going to use big brackets here to contain everything that I'm going to get for that product rule. So the product rule would be the first function x times the derivative of the second function y. The derivative of y wants to be a 1, but that gets multiplied by a y prime. Plus the second function, which is our y, times the derivative of the first, and the derivative of x is just a good old 1. So here is the derivative of our outer function, that square root, times the derivative of our inner function, which is that product rule. So that takes care of the derivative of that whole left side. Now we want to take the derivative of the right side. Derivatives of x's you do normally, derivatives of y you do normally but multiply by a y prime. So derivative of x goes to 1. Derivative of a minus 2y wants to be a minus 2, but we have to multiply by a y prime. So let's clean this up a little bit. When I see a negative exponent, I know that that can flip this xy down to the bottom, and since it would become a positive 1/2 power, that's the same as a square root. So I'm going to go ahead and change this xy to the negative 1/2 to a 1 over square root of xy, and this 2 that was out front from my fraction can be in the denominator still. So that's all this outer stuff. And then in these brackets, x times 1 times y prime is just x y prime, and then we get a plus y. Now I know that I want to get these y primes together, but I can't get at this y prime in the brackets until I get rid of what's out front. Now you could distribute, but it's going to get kind of messy because we'll have this fraction everywhere. So what I might suggest is getting rid of this fraction right away by multiplying by that denominator on both sides. So that means I'm going to have to take everything on this right side times that 2 square root of xy. The left side will just cancel out that fraction, giving me x y prime plus y. And on the right side, when I distribute that 2xy on the radical across, I'll get 1 times 2 square root of xy, which is just 2 square root of xy, minus 2 times 2 is 4 square root of xy, and then that y prime. So this term has a y prime. This term has a y prime. I want to get them together. So I'm going to add this 4 root xy y prime over to the other side. And this y does not have a y prime, so I am going to subtract it over to the right side. So this will be gone over here, leaving me just an x y prime plus 4 square root of xy y prime. So there's my left side. All my y primes are together. And on the right side, these are gone, so I'm left with 2 square root of xy minus that y that I moved over. Now that I have my y primes together, I can factor it out. So I'll be left with an x plus 4 square root of xy. And last thing I need to do is just divide by the stuff in parentheses. So my final answer will be y prime equals 2 square root of xy minus y over x plus 4 square root of xy. Okay? All right, the next example, another tricky one, and this time we have some sines and cosines involved as well. So we've got an implicit function because the x's and y's are mixed together. So what I want to do is that implicit differentiation. So I'm going to take the derivative with respect to x of the left side and the derivative with respect to x of the right side. Now the left side is the tricky part because you have to recognize that this is 2 sine x times cosine of y. So we need to apply the product rule again on that left side. Now what do you do with that 2? You can either leave it out front and then in parentheses do your product rule, Or what I typically do is I just think of this 2 sine x as my first function, so I sort of group that 2 with the sine, and then I think of my cosine of y as my second function. So I'm going to do the first function, that 2 sine x, times the derivative of the second function. And here you need to use that chain rule. The derivative of the outer cosine wants to be a minus sine of that y, but because there's a y, we need to take the derivative of that y and multiply by it. So that's that y prime. So we have first times derivative of the second plus the second function was our cosine y times the derivative of our first. The 2 will stay there, and the derivative of sine x is just cosine x. And on the right hand side, derivative of 1 just goes to 0. So the only term that I have that has a y prime is this big first term. So let's clean this up a little bit. I'm going to group together that minus and that 2 and make this a negative 2 sine x sine y times y prime plus a 2 cosine x cosine y equals to 0. Now I want to get the y prime term by itself. Since it's negative, let's go ahead and add it over to the other side so that it becomes positive. Okay, so this is going to become 2 cosine x cosine y equals 2 sine x sine y times y prime. And since there's only the one y prime term, all I have to do is divide by all these coefficients of that y prime. So I'm going to divide both sides by the 2 sine x sine y. I'm going to divide by all 3 of those terms simultaneously. So y prime will be, the 2's cancel out, and notice that cosine over sine is cotangent of x, and cosine y over sine of y is cotangent of y. So we could simplify it by changing to cotangents. And there is our derivative. Okay, next example. X equals secant of 1 over y. So we have our x's and y's kind of mixed up. We don't have it y equals 2, we have it x equals 2. So it's an implicit function again because we don't have that y by itself. So I'm going to go ahead and take the derivative with respect to x of the left side and the derivative with respect to x of the right side. Now when I see that 1 over y, I immediately think of how am I going to take the derivative of a 1 over y. Eventually we'll need to do that. And probably the best way to do that would be to move that y up and change it to a y to the negative 1. So I'm going to go ahead and write this as secant of y to the negative 1. So when I take my derivative of the left side, since it's an x, I'm just going to get a 1. Nothing special over there. But on the right side I have that y term, so I am going to need to use that chain rule and get a y prime. But before I can get to that, I've got to take my chain rule and take derivatives from the outside in. The outermost function here is that secant. What's the derivative of a secant? Well, it's secant tangent. So we need secant and tangent multiplied together, but it's going to be secant of whatever I have right here times tangent of whatever I have right here. So this is actually going to be secant of y to the negative 1 times tangent of y to the negative 1 times, that's the derivative of the outer function. Now we need to do the derivative of the inner function. What's the derivative of y to the negative 1 with respect to x? Well, the derivative of a negative 1 power, you would bring the power down, and then you would subtract 1 from the power, so it would become y to the negative 2, and then the derivative of the y part is where that y prime comes in. So we took the derivative of the secant, we took the derivative of the negative 1 power, and we took the derivative of the y, and we multiplied all of those things together. So if we rewrite this a little bit, clean it up a little bit, we're going to have a 1 equals, If you want, at this point, you can change that y to the negative 1 to a 1 over y. So this would be secant of 1 over y, tangent of 1 over y. And then this negative 1 over y squared, I could put the negative out front of my secant and put that y squared in the bottom. And all of that is being multiplied by my y prime. So to get y prime by itself, we're just going to need to multiply by the reciprocal of this, which when you multiply by that reciprocal over on the left-hand side and multiply it by 1, you're just going to get that reciprocal right back again. So y prime will be this reciprocal y squared over negative secant 1 over y, tangent of 1 over y. And there's varying things you could do with this. A 1 over a secant is a cosine, so you could change this to a negative cosine of 1 over y. And 1 over tangent is a cotangent, so you could change this to a cotangent of 1 over y. And then that's all getting multiplied by my y squared. And I could even put that y squared in front with that negative out front. So either of these answers would be correct. Okay? All right, the next one. X cosine y equals to 1. Find dy dx at the point 2 comma pi over 3. So same thing as before. Take the derivative, but this time we're going to plug in a point at the end. So to find the derivative of this, because the x's and y's are together, we're going to need to use that implicit differentiation. So I'm going to take the derivative of the left-hand side and the derivative of the right-hand side. Be careful on that left-hand side. This is x times cosine y, so you must use a product rule on that left-hand side. So the first function is the x times the derivative of the second. The derivative of a cosine y wants to be a minus sine y, but because it had a y in it, we need to multiply that by a y prime. So there's first times derivative of the second plus second times derivative of the first, which we just want to be a 1. And derivative of 1 is just 0. So we get negative x sine y, y prime, plus cosine y equals to 0. Let's move this y prime term over to the other side to make it become positive. So we get cosine y equals x sine y times y prime. And to finish solving for y prime, we can divide by x sine y on both sides. So we have cosine y over x sine y. If you wanted to change that to a cotangent of y on top and leave that x in the bottom, you could certainly do that. So now that we have this derivative, we're going to plug in our point, and we're going to need to use both the x and the y values in this function that we just came up with for our derivative. So I'm going to put the 2 down here in the bottom, and then I'm going to put the pi over 3 in for these y's. So y prime becomes cosine of pi over 3 divided by 2 times sine of pi over 3. And you need to remember your unit circle. Remember that pi over 3 is the same as 60 degrees, and a cosine of pi over 3 is a 1/2, whereas a sine of pi over 3 is a root 3 over 2. So when I simplify, these 2's are going to cancel. So this is going to become 1/2 over root 3, or root 3 over 1, and I'm going to want to multiply by that reciprocal. So I get 1 over 2 root 3. If you want to rationalize your denominator, you could multiply by some root 3's and get root 3 over 6. You don't have to do that, but it's an option. All right, so dy dx is square root of 3 over 6 at this point. Okay, next example. Find the equation of the tangent line to y squared equals x minus 1 over x squared plus 1 at the point 2 comma root 5 over 5. So we want to find the whole equation of the tangent line. So we need to find the slope of the tangent line first, and that is the derivative. So we want to find the derivative of this function. And I'm going to go ahead and take the derivative of the left side with respect to x and the derivative of the right side with respect to x. So the left side, y squared, that derivative wants to be a 2y, but we have to multiply it by a y prime because it's a y term. The right side is a fraction, so the only way to take that derivative would be to use the quotient rule. Fortunately, all of these are x's, so we're not going to have any y primes being multiplied, but we just need to make sure we use the quotient rule correctly. So we're going to do low, which is the x squared plus 1, times d high is 1, minus high, which is x minus 1, times d low, and the derivative of the bottom wants to be a 2x, all over low, the bottom squared. So we get 2y, y prime equals, let's clean up that numerator, we're going to get an x squared plus 1. I want to distribute my negative and my 2x across. So this is going to become a negative 2x squared. A minus times a minus becomes a plus, and we're going to get plus 2x. So we have 2y, y prime equals x squared minus 2x squared is a negative x squared plus a 2x plus a 1 all over x squared plus 1 quantity squared. And finally, to solve for y prime, we would just want to divide by 2y, so I can stick that 2y in the denominator that I already have on that right hand side. So y prime is going to be negative x squared plus 2x plus 1 all over 2y times x squared plus 1 squared. So there's my derivative at every point. The next thing I need to do is to plug in my x and my y for this particular point. So the x's are going to become 2's, and this y down here will become root 5 over 5. So let's see what that gives me. Negative 2 squared plus 2 times 2 plus 1 over 2 times root 5 over 5 times 2 squared plus 1 quantity squared. So we get negative 4 plus 1 over 2 root 5 over 5 times 2 squared is 4, 4 plus 1 is 5, 5 squared is 25. So 5 will cancel into that 25 5 times, leaving me 2 root 5 times 5, or 10 root 5 in the bottom. Since these 4's cancel, I have a 1 on top. And you probably want to rationalize your denominator here because we are going to be doing something with this. So we'll get root 5 on top, and on the bottom will become a 50. So there is my m, root 5 over 50, and we have our point 2 comma root 5 over 5. So our equation of our tangent line is just going to use that point slope form. So y minus the y coordinate equals our slope times x minus the x coordinate. So that's y minus root 5 over 5 equals square root of 5 over 50 times x minus square root of 5 over 2 will go into that 50 25 times. And then to finish it off, I'm going to add root 5 over 5 to the other side. So I get y equals square root of 5 over 50x. And if you wanted to get a common denominator here of 25, this top fraction already has it. The bottom fraction, we'd have to multiply the top and the bottom by 5, so it would be 5 root 5. So a negative root 5 plus a 5 root 5 would be a positive 4 root 5 over 25. And there is our tangent line equation. Okay, so yucky numbers, but doable, just a lot of algebra. All right, the next example here is a pretty common one. So this is something you're going to want to remember because you're going to have to replicate it quite often. It's a question that's asking us to find the vertical and horizontal tangent lines. So to find tangent lines, you know that you need to find a derivative because that's a slope of a tangent line. So before we even worry about vertical or horizontal tangent lines, let's go ahead and find our derivative. So the derivative requires using implicit differentiation on this problem because we have the x's and the y's mixed together. So let's find the derivative of the left side and set it equal to the derivative of the right side. Derivative of x terms you do as normal. Derivative of y terms you do as normal but multiply by a y prime. So derivative of 4x squared would just be 8x. Derivative of y squared wants to be a 2y, but we multiply that by a y prime. Derivative of negative 8x is just negative 8. Derivative of 4y wants to be a 4, but we multiply by a y prime. Derivative of 4 goes to 0, and derivative of 0 stays 0. So these two y prime terms will stay put. And the 8x I'm going to subtract over to the right side, and the negative 8 I'm going to add over to the right side. Then I'm going to factor out my y prime. And finally, I'm going to divide by that 2y plus 4. Now you can do a little bit of simplifying on this right-hand side, and that's only because every single one of these terms, all four of them, are divisible by 2. So I'm going to divide each term by 2 on top and bottom. So this becomes a negative 4x plus a 4 over a y plus a 2. Now if any one of these four was not an even number, then you wouldn't be able to simplify at all. It has to have every term being divisible by the same number. All right, so here's our derivative. Now let's think a little bit about the question that's being asked. We want vertical and horizontal tangent lines. So think about a vertical line. What kind of a slope does a vertical line have? Well, if it's vertical, it has no slope, or in other words, its slope is undefined. What kind of slope does a horizontal line have? Well, a horizontal line always has 0 slope. So if we look at our derivative, which represents the slopes of all of our tangent lines, when is this fraction going to become a no slope? When is it going to become undefined? Well, the only way a fraction becomes undefined is when the denominator becomes a 0. So to find our vertical lines, what we're going to do is we're going to set just the denominator to 0. And this will find for us the vertical tangent lines. So to find vertical tangent lines, set the denominator of your slope equal to 0. Now think about horizontal tangent lines. When are your slopes going to be 0 if you have a fraction? When is a fraction equal to 0? The only way a fraction can equal to 0 is when the numerator is 0. So to find horizontal tangent lines, we're going to set the numerator equal to 0. So when the top is 0, we have horizontal tangent lines. When the bottom is 0, that makes it undefined, so that's going to give us our vertical tangent lines. So let's do both. So we're going to do our horizontal tangent lines by taking that numerator, negative 4x plus 4, and setting it to 0. And if we solve that, we're going to get that x is 1. Then for the vertical tangent lines, we're going to set the denominator, which is y plus 2, equal to 0, which tells us that y is negative 2. Now we're not quite done, because the question is asking us to find the points at which this graph has horizontal and vertical tangent lines. So when I say that x is equal to 1, that's not a point, that's just the x value of the point. So we need to find out the y values that correspond to this x value. So if you ever want to know your y values, you always need to go back to the original curve, the original equation that you started with. And we're going to plug in 1 for each of these x's and then solve the remaining equation for y to tell us the y values that go with x being equal to 1. So we're going to plug in 1 up here for these x's. So that would give me 4 times 1 squared plus y squared minus 8 times 1 plus 4y plus 4 equals 0. So that's going to give me 4 plus y squared minus 8 plus 4y plus 4. 4 plus 4 is 8, and that's going to subtract out the 8 we have in the middle. So this becomes y squared plus 4y equals to 0. And to solve that, we can just factor out a y. And that tells me that y is either 0 or negative 4. So that means when x is 1, we actually get 2 different y coordinates. So we are going to have 2 points where there are horizontal tangent lines. And they are going to occur at the points where x is 1 and y is 0, or x is 1 and y is negative 4. Okay, now we're going to do that all over again, but this time we're going to do it for the vertical tangent lines. And remember, for those, we found out that that happens when the y is 2. So now we're going to go back to this original equation again, but this time we're going to let y be 2, and we're going to solve for x. So this equation would become 4x squared plus negative 2 squared minus 8x plus 4 times negative 2 plus 4 equals 0. So that's 4x squared plus 4 minus 8x minus 8 plus 4 equals 0. Again, the 4 and the 4 make 8, which cancel the 8 that we already had. So we get 4x squared minus 8x. I can factor out a 4 and an x, and that leaves me with x minus 2. So either x is 0 or x is 2. So our vertical tangent lines are going to occur at 2 points as well. When x is 0, the y was negative 2, or when x is 2, the y was negative 2. So we have 2 points on our curve where we have vertical tangent lines, 2 points on our curve where we have horizontal tangent lines. All right, the next example, something a little tiny bit different. This time we want to find y double prime if x squared plus 25y squared is equal to 100. So we want a second derivative. And you can't find a second derivative until you've found a first derivative. So let's go ahead and find our first derivative by using implicit differentiation. So I'm going to take the derivative with respect to x of this left side, the derivative with respect to x of the right side. Derivative of the x terms is business as usual, right? Derivative of x squared will just be a good old 2x. Derivative of y terms, you take the derivative as normal but multiply by y prime. So the derivative of 25y squared wants to be a 50y, and then we multiply that by a y prime. Derivative of 100 goes to 0. So if I subtract this 2x over to the other side to get this y prime term by itself, then I can just divide by 50y, and that tells me that y prime is negative x over 25y. So there's our first derivative. Now, how do you find a second derivative once you have a first derivative? Well, you just take the derivative again. So we're going to take the derivative with respect to x of that first derivative and the derivative with respect to x of its formula. So I'm just doing implicit differentiation again, but on this result that we just found. Now, if you think about y prime, that's also dy dx. So the derivative with respect to x of dy dx is just that notation d squared y over dx squared, otherwise known as y double prime. So the derivative of y prime is just y double prime. So the left side is nothing too special or too complicated. The right side has x's and y's, so we are going to need to be careful there, and it's a fraction, so we are going to have to use a quotient rule. So the quotient rule will be the low, which is 25y, times d high. The derivative of negative x is just negative 1, minus high, that negative x, times d low. The derivative of 25y wants to be a 25, but we need a y prime in there because it was a y term, over the bottom squared. So simplifying here a little bit, we get negative 25y minus minus becomes plus 25x y prime over 625y squared. Now all of these terms are divisible by a 25, so if you want, you can go ahead and get rid of that common factor. So this would become negative y plus x y prime over 25y squared. Now, one last thing. If you look at this answer, it's got x's and y's in it, but it also has a y prime in the answer. And you don't really want to leave that y prime in there because we know exactly what y prime is. We know that y prime is negative x over 25y. So when you're finding these second derivative problems, you're always going to want to substitute in what that first derivative is, because usually you'll need it in your formula. So I'm going to replace this y prime right here with negative x over 25y. So this will look like negative y plus x times negative x over 25y all over 25y. And this actually makes it worse because now you have a fraction within a fraction. So an easy way to simplify complex fractions is to multiply by the denominator that you want to get rid of. And this is the denominator that I don't want to have. So I am going to multiply the top by 25y, and to balance it out, I'm going to multiply the bottom by 25y as well. Now when I do that, I have to make sure that I multiply that 25y times this negative y as well as all of this stuff, and then to the bottom as well. So negative y times 25y is negative 25y squared. We have this minus, so I'm going to go ahead and pull that out front. This 25y cancels that 25y, leaving me just my x times my minus x, which is that negative x squared. And on the bottom, 25y times 25y squared is 625y cubed. So when you're finding these second derivatives, you want your final answer only to be in terms of x's and y's. You shouldn't have any y primes still in your answer because you can always substitute in what y prime was equal to. All right, the next one. X squared plus y squared is equal to 9. Find the equations for the tangent line and the normal line at the point 2, square root of 5. Now we know that x squared plus y squared equals 9. That's just a circle with a radius of 3. So let's visualize what we're talking about here. 2, root 5 is somewhere over here. And you all can visualize what this tangent line would look like, something like that. And it's going to have some slope m, which we know how to find because the slope of that tangent line would just be the derivative of this curve with this point plugged in. Now what is a normal line? A normal line, by definition, also goes through this same point, and that's the only point on the circle that it will go through, but it's perpendicular to our tangent line. So this is called our normal line. And the relationship that it has is its slope should be the perpendicular slope to the slope of our tangent line. And you should remember, hopefully from algebra, that perpendicular lines have opposite reciprocal slopes. So if we can find this slope m, then we just take the opposite reciprocal and we now have the slope of our normal line. And they both go through this point 2 comma root 5. So we'll have a point, we'll have a slope, so we can find an equation. So that's going to be our process. Now all of this depends on being able to find that tangent line slope, which is a derivative. So let's find the derivative of this circle. It's defined implicitly, so I'm going to take the derivative implicitly as well. So the derivative of the left side equal to the derivative of the right side. Now the derivative of x squared is just 2x. The derivative of y squared wants to be a 2y, but we multiply that by a y prime, and the derivative of 9 goes to 0. So if I subtract that 2x to the other side, it becomes negative, and then I can just divide by 2y. Those 2's will cancel, and I get negative x over y for my derivative. So at the point 2 comma root 5, this tangent line slope will just be negative 2 for the x, and the y becomes square root of 5. If you want to rationalize that denominator, you would get negative 2 root 5 over 5. So either one is correct. Now for the normal line, we want the opposite reciprocal slope because these lines are supposed to be perpendicular. So what is the opposite reciprocal of negative 2 over root 5? Well, you just flip it over and use the opposite sign so it becomes positive. So now we know the slopes of each and we know a point for each, so we should be able to come up with our equations. So let's start with our tangent line. Our tangent line equation will be y minus this y coordinate, square root of 5, equals our slope. And I'm going to use this rationalized slope just because it's easier to simplify with, times x minus the x value 2. And when I distribute, I'm going to get negative 2 root 5 over 5 times x. Minus times minus becomes plus, and then this is 4 root 5 over 5. And then I'm just going to add that root 5 over. And if you want to get a common denominator, you can here. This would become 5 root 5 over 5. If I multiply by 5 over 5 to get my common denominator, so I'm going to get a 4 root 5 plus a 5 root 5 is a 9 root 5 over 5. So there's the equation of my tangent line. Now we're going to do exactly the same process, but for our normal line, we're just going to use that opposite reciprocal slope. So we're still going to do y minus our y coordinate root 5 equals our slope, and this time I'm using root 5 over 2 times x minus the x coordinate. When I distribute, we're going to get root 5 over 2 times x minus, these 2's will cancel and I'll just have a root 5. So when I add that root 5 across, they actually end up canceling on both sides. So my normal line is just y equals square root of 5 over 2 times x. Okay, the last thing that we're going to talk about may seem initially very different, but it's a new process that's going to help us to find derivatives a lot easier, and it's going to involve using some implicit differentiation. But this process is called logarithmic differentiation. And the idea is that sometimes you're going to be given equations that may actually start out explicit, like this equation right here is an explicit equation. But this right-hand side is very, very complicated. So to take the derivative of this right away would be a whole lot of work, because you would have to use a quotient rule because you have this big fraction. You also have a product in the numerator, so you would need a product rule, and on top of that you would need a chain rule for the square root and a chain rule for this quantity squared. So there would be a lot of work to do to figure this out. So what we're going to do instead is we're going to use logarithms to help us break apart this complicated function, and that will hopefully simplify it so that when we take these derivatives we'll have a much simpler equation. So the first step of logarithmic differentiation is to take the logarithm of both sides. Now you can use the log of any base that you want, but since in calculus derivatives are much simpler when you use base e, you typically will be taking ln's of both sides. So we're going to take the ln of the left side and take the ln of the right side, and as long as you do it to both sides you're keeping it balanced. Now the reason we do this, the reason we take the ln of both sides, is because we're going to apply some properties. And the properties of logs that we're going to be using are properties of quotients. So things like the ln of a divided by b becomes a difference of ln's. So ln of a minus ln of b. We're also going to be using the ln of a product, which becomes the sum of two ln's. And finally, we're going to be using the ln of a raised to the b, this power rule, where you get to bring that power b down out front and multiply it by your log. So I'm going to use these three properties to break up this great big function right here. So what this is going to do for us is, since I have a product on top, that's going to become a sum of these two pieces. So the left side will stay ln of y, but the right side is going to become ln of the first piece, which is that x cubed, plus the ln of that square root of 1 minus x. And the 2x plus 1 quantity squared, that was in our denominator of our quotient, so that one gets subtracted. So any piece of this function that was in the numerator should be a positive ln. Any piece of this that was from the denominator should be a negative ln. Now the last thing I'm going to do is I'm going to bring my powers down. So this cube will come out front, this square will come out front, and the square root is actually a 1/2 power as well, so that can come out front. So this becomes ln of y equals 3 ln of x plus 1/2 ln of 1 minus x minus 2 ln of 2x plus 1. Now, not once have I taken a derivative. The only thing I did was take an ln of both sides and then apply these different properties. So now is where I am going to use some derivatives. I'm going to be taking the derivative with respect to x of the left side and the derivative with respect to x of the right side. That's that implicit differentiation. Whenever I take the derivative of a log, the rule that we're using is the derivative with respect to x of ln of stuff is stuff prime over stuff. You put whatever this argument is here in the denominator, and by the chain rule you multiply that by the derivative of that stuff. Okay? So we're going to be using that rule for each of these four ln's that I have in my problem. So starting with the ln of y, the derivative of that with respect to x. Notice that this is a y term, so we're going to need a y prime in our answer. So the stuff is this y, so that goes in the bottom, and the stuff prime is that y prime, so the y prime goes in the top. So there's my stuff prime over stuff. Okay, that will be what the left side will always look like when you're doing logarithmic differentiation. On the right side, we're just going to go term by term, and each of these are x's, so I don't need any y primes anywhere on this right-hand side. So the 3 will stay there, And the derivative of ln of x is just 1 over x. Remember, x is the stuff, and the derivative of x is 1, so that's why there's a 1 on top. In the middle, the 1/2 will stay there. The stuff is this 1 minus x, so that goes in the bottom. And the derivative of that stuff should be a -1 because there's a minus in front of that x, so be careful there. And then the last one, the 2 stays put. The stuff is this 2x plus 1, so that goes in the bottom. And stuff prime, the derivative, would just be 2, so that goes on top. Now cleaning it up, we get y prime over y equals 3 over x. I'm going to take this negative and turn this into a minus sign, so this becomes 1 over 2 parentheses 1 minus x, and then minus 4 over 2x plus 1. Now we're almost done, except we want to know what y prime is, because that's what the word differentiate means. And this isn't just y prime, it's y prime over y. So how do I get y prime by itself? Well, I need to undo this division by y, and I can do that by multiplying both sides by y. And that means I need to multiply this entire right side by y. So y prime will be 3 over x minus 1 over 2 parentheses 1 minus x minus 4 over 2x plus 1. And the very last thing I'm going to do, you could write a y there, and there's technically nothing wrong with that, but we know what y is because on this problem the y was actually defined explicitly. So instead of writing y right here, what I'm going to do instead is rewrite the original function, which was what y was equal to. So it looks a little bit messy, but it leaves your answer entirely in terms of x's, which is sometimes a nice thing. So there is my derivative. Okay, so to summarize, we took an ln of both sides, then we broke down that right-hand side using properties of logs. We took the derivative of each side using the chain rule and using stuff prime over stuff. Then we multiplied both sides by y and substituted in what y was equal to. Okay? All right, the next one. Y is equal to x raised to the x minus 1. Now this is an example where sometimes it's hard to know what to do. We have rules for how to take the derivative of something like x squared or x cubed or x to the 4th, where x is being raised to a constant. We also have derivative rules for taking derivatives of things like 2 to the x, 3 to the x, e to the x, where the base is a constant and the power is the variable. We don't have any rules when the base is a variable and the power is a variable. There's no derivative rule for that. So the only way to handle a problem that's a variable raised to a variable is to use this process called logarithmic differentiation. So let's see why this process works. Step 1, take the ln of both sides. So this becomes ln of y equals ln of x to the x minus 1. Now normally at this point we want to use our properties of logs to help us out. So the only property of logs that I can use on this right hand side is to bring this power down. And when you do that, you want to make sure that you use parentheses around it, because it's that x minus 1 times the ln of x. Now that we've brought our power down, we can go ahead and take a derivative. So I'm going to take the derivative with respect to x of the left side and the derivative with respect to x of this right side. Now the derivative of the left side will always be the same. We're going to use stuff prime over stuff. This y is the stuff, so that goes in the bottom, and the derivative of that, which is our y prime, goes on the top. For the right hand side, be careful. This is x minus 1 times ln of x. So that means you must use a product rule here. So we're going to do the first function, which is that x minus 1, times the derivative of the second. And the derivative of ln of x is just 1 over x. That's its definition. Plus the second function, which is our ln of x, times the derivative of the first. The derivative of x minus 1 is just a 1. So cleaning it up just a little bit, you can do this many different ways. I'm just going to go ahead and take that x minus 1 and put it all over x, and then that's being added to our ln of x. And to finish it off, we're trying to find out what y prime is, so I want to multiply both sides, and that includes this whole right side, times that y. So the y prime will be by itself, and the left side is x minus 1 over x plus ln of x, and I'm going to substitute in what y is. Remember, y was defined to be x to the x minus 1. So that's my last step, and there's my derivative. Okay, one last example. Find the derivative of y equals sine of x raised to the 1 over x. Now this is just like the last example in that we have a variable in our base, part of this sine of x, and then we have a variable in our power. Our power here is that 1 over x. So this is a variable raised to a variable. And that means we want to be using that logarithmic differentiation. Okay, so your first step is going to be to take the ln of the left side and the ln of the right side. And the whole reason we do that is so that we can take that variable power and bring it out front. So this becomes 1 over x times the ln of sine of x. Now you can do this any number of ways. I am just going to take this x, this 1 over x that's out front, and take it underneath my ln of sine x. So I'm just going to shift this x underneath like that. So these two lines are equivalent. I just made it into a quotient instead of a product. And that way I can go ahead and use my quotient rule. So we're ready to take our derivatives of the left and the right side. The derivative of the left side, the derivative of ln of y wants to be a 1 over y, but we have to multiply that by a y prime. So your left side will always be y prime over y. On the right side, we need a quotient rule because I set mine up to be a quotient. So we're going to do the bottom, the low, times d high. Now you have to be careful on the derivative of the top. This is going to be stuff prime over stuff. So my stuff is this sine of x, so that goes in the bottom. And stuff prime would be the derivative of sine of x, which is cosine x. So there's low d high minus high d low, and the derivative of the bottom is just a 1. All over low, so x squared. So we get y prime over y equals x times, now I'm going to go ahead and change this cosine x over sine x to a cotangent x. That way I don't have a fraction within a fraction. So I have x cotan x minus ln of sine x all over x squared. And I want to solve for y prime, so I'm going to multiply both sides by y so that these will cancel out. And then I'm going to take this entire fraction times that y. So x cotan x minus ln of sine x all over x squared. And the last thing I'm going to do is replace y with what it's equal to, which is sine of x raised to the 1 over x. And all of that big mess is my derivative. All right, good job. That concludes our lecture on implicit differentiation. Good luck.